In lecture, I believe 11, we took a couple quizzes, we went over a little bit of homework, and now we are going to go over the homework. How was the homework that was due today? I thought it was kind of chill, right? Yeah. You guys had to watch a video, that took a long time. Yeah, yeah, so wait, what happened? You guys had to watch the practical video, is that right?
And reciprocal and quotient.
Was that kind of a fun lecture? I thought it was.
The tyranny of the blue text.
The tyranny of the blue text, yeah. It was like, it was really in there, right? It was the tyranny, yeah. I know. You thought it was just a little bit. And they even make this terrible, comment. Did you see this? It was like the worst thing ever. It was, I was not exaggerating. They're like, so basically sometimes proofs make sense. And this is one of those times when you just better shut up and do what we say. The exact quote is, some mathematical proofs are straightforward. Others involve clever steps that may appear unmotivated to a reader. That's because they are unmotivated to a reader, because you didn't write it correctly. This proof involves such a step. So we're just going to do it in blue, and you're just going to get over it. It's terrible. Can you believe that they didn't include the beautiful picture with the rectangle? It's like, it's terrible. All right, good thing you have me. So anyway, now that we know the parabola, we know the quotient rule, we know the reciprocal rule, now there's lots and lots of things which we know how to differentiate. And one of the things you had to do for homework was to come up with a formula for the derivative of secant, which you can easily do by representing it as 1 over cosine. Well, can you close the window? You have to be pretty strong though.
I know, I've heard.
And the derivative, you gotta go up high, then down hard. Like, you have to be tall too. No, it's not good. Arun's got it. Arun's got it. Using the reciprocal rule, the derivative of 1 over cosine is the opposite of the derivative of cosine over the cosine squared. And we get secant tan. These should be, you gotta go all the way up, and then with 2 hands, go high, all the way to the top, and then down hard. Yeah. That's the only way to close it. Alright, so the formula is secant tan. I basically recommend memorizing this, but like honestly, if you forget it, or if you panic that you have not memorized it correctly, you can rederive it in like 30 seconds. So it's like one of those kind of combinations of kind of memorizing / rederiving it as needed. Cosecant, basically same thing. Reciprocal rule says it's the negative of the derivative of sine, which is negative cosine over sine, and we get negative cosecant cotan. This is how normally people usually write it. And for cotan, we're going to use the quotient rule. We do exactly what this person says. We represent cotan as cosine over sine, and then it's derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. And that turns out to be that, which can be that. Oh, interesting. This person did it like that. I just think of that numerator as being -1 because sine squared plus cosine squared is 1. But I guess this is the same thing. That's negative. Yeah. Check. 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 Do you guys see what I'm talking about? That's the way. It seemed to make the most sense to me. Is if you factor a negative out of the numerator, that sine squared plus cosine squared is 1. But this way works also. Anyway, answer is negative cosecant squared. Oh, by the way, while we're on the subject, do you guys know there's like a song for the quotient rule?
Heidi.
Have you heard the song?
Mr. Paul sings it, doesn't he?
Yeah, I just found that out. So, I find this stuff kind of annoying and obnoxious because I just know the quotient rule and I just know it and that's it. But some people like songs, so there's a song that goes like this. If you're taking the derivative of 2 functions, of the quotient of 2 functions, there's the function that's up high and there's the function that's down low. And so the derivative of this is, so it's the low function times the derivative of the high function minus, it's not a song yet, so minus the high function times the derivative of the low function. And then that's over, there's not an X squared. So it's not really a song, it's more of like it's like a Seven Dwarfs, you know how they sing, what's that song they sing when they go marching?
Off tour.
Hi ho, hi ho, it's off to work we go. Yeah, okay, so that's a song. This is not really like that, I decided. But here's what it is. Here's how you pronounce this as low d high, high d low, over denominator squared we go. high d low over, I don't know what the tune is, over denominator squared we go. And what's nice about it is if you accidentally, because the nice thing about the product rule is that it's symmetric, but the quotient rule is not symmetric, right? So if you're going to screw it up, you're going to pretty much get the negative in the wrong place. So if you accidentally begin to write the derivative for the quotient rule like this, now this gets pronounced as low d high, high d. Wait, isn't that right?
You,
I said it wrong.
you switched your F and G.
What did I do? Oh man! Oh man! So wait, but now is it? Is this proving it's wrong?
Now it's wrong.
Now it's wrong. Good. So now this says high d low, low d high over denominator squared we die. And this is some crap that Mr. Stein made up like 12 years ago. And what I think is really weird is that Mr. Paul, who is Mr. Stein's student, he graduated the year before I started teaching here.
Oh my gosh, that's so creepy. That's so
What if you would like Mr. Hall's like a
Well,
student
don't
and
you
you
think
were
it's
like
more creepy that he was Mr. Stein's student? Like that's pretty creepy, right?
No, but I mean like
student.
Mr. Stein's a little bit older than you, so
Pretty old. All right. Wait. So he has a where'd it go? He has a man. Where is it? Oh, yeah, here we go. So they sang a. This is the wrong one.
This is so creepy.
This is the correct one. So Stein used to play that every year, but I never. And he always was like, "Oh, he was one of my former students," but I didn't know that it was the great Paul.
wait, that was
Okay.
him singing?
Yeah, that was him singing.
Mr. Paul's really good at
He
singing.
recorded like whatever.
Mr.
He's
Paul's
really
great
good
at
at
everything. He needs to stop.
All right. The point is, that's like a little trick for memorizing the quotient rule. Good. Anyway, we're back. Basically, I don't know. We don't need to go over all these problems. I feel like they're all mostly straightforward. Kind of just do it, right? Take some derivatives. Things happen. Should we just like take a minute and look up and check all these? Do we agree with that they're all right? I don't know if I do. First, shouldn't this be squared? I guess they were mostly odds anyway, and they were in the back of the book, but for the even ones, looks pretty good. Oh, notice whoever did number 18, who did number 18?
Me.
Emma is doing an advanced move called I hate the quotient rule, and basically is just not using it here because she just doesn't feel like it, and writing it as x to the negative 1 and then using the product rule. So that's like an option sometimes. Were there some of these that you thought were hard that we need to spend time on? Magna, you want to do one? No? All easy? Yeah, I thought so. It was relatively chill homework. All right, so take a minute and check these. If you have a question, ask now. Otherwise, I'm going to collect this homework. This is the easiest unit of the whole year, because it's really just like, take the derivative of stuff. More or less minus it. That kind of we good?
Wait,
Kind of
you
somewhere.
also said that the hardest problem we've done all year was in this unit.
Oh yeah. Coincidentally, it's a little tight.
Wow,
but,
this is-
More back top pieces. All right. Can I get? No, not the hardest part of the year so far.
Well, it can also be on average.
Yeah, it could be on. It could be like. Yeah, it could be like. All right, good. So can I have all the homework right here? Please, next to Raymond. And then, can I also have my fancy double-sided pencils back? There's no way you're getting out of here with those. I throw over there. I put over there.
Wait, you need the back.
And then have a task for you up front. So, get out a first piece of paper notes. Good, if we can call the quiz if you want. Quiz number 3.
Wait, can we actually do it?
Do these 2 things. Go.
What thing?
Thing 1, thing 2.
Sorry?
Yeah, I got it. You can just, no, you can do it in your notes.
Can you take this one?
You can just do it in your notes.
Just use the down.
I want to do one. They'll like bring it back to bed.
Yes.
So remember when we proved the power rule, and I told you that even though our proof only applies for positive integers, that it also works for negative integers and also fractional integers, but I would like get back to that later. So I'm partially getting back to that now. And now that we know the reciprocal rule, it's pretty easy to prove that the power rule also works for negative exponents. So just take like a minute and do that. Let's take thing 3.
Just do the reciprocal, yeah, for whatever it's
Yeah. Oh, okay, so it's pretty much is derivative, but of like 1 over.
Yeah, so if you did it with
The
one,
after
you could just derive it. I know this because
And if you ever forget that, just think that you have like the multiply together, and then let's get it multiplied together.
So pretty much the derivative.
Oh, you're doing it using the definition of the derivative, but actually we don't use the
Derivative to find.
Oh, no, for the first one? Oh, for the second one. Did you just write really small, didn't even see it? Oh, yeah. Yeah, it's like one line, right? So the derivative of the reciprocal of 1 over x to the n is, we now know, just the derivative of x to the n over x to the n squared. Is this what you guys did, basically?
Yeah.
Or am I going too fast? I am going too fast. Okay, yeah. So then this is now, but now n is positive. That was kind of like the assumption here, is that n is a positive integer. So now I can just apply the normal product rule, or power rule, which we proved with the binomial theorem, and the other way too. This becomes negative n x to the n minus 1 over x to the 2n. And now I just apply some exponent rules, right?
Yeah.
Yeah.
Subtract 2n.
So this is negative n x to the n minus 1 minus 2n. So that's negative n x to the negative n minus 1. Ta-da! Which is exactly what I would predict the answer would be if I had just had been assuming that the power rule works, which is what we have been doing. Cool? Alright, I feel like that's not really deep or exciting. Might have been in the book too. Was this in the book? I feel like it might have been in the book. Alright, thing 2 is an awesome thing. And almost no one does it. This is due to Mr. Giles, actually. I never used to do this, but now I do it this way. The derivative of natural log. We can actually do this right now using the definition of the derivative. Yeah, do it. You want to get anywhere? Oh, yeah.
In what sense?
Kind of need to know some things about logs.
Like thermal.
Like some basic.
Like the
Basic.
addition log.
Is that?
We'll do some review for the algebra 2 part. Oh, no, you guys want to take algebra 2.
gosh.
So maybe you should be taking it. Yeah, so facts about logarithms, right? The ln of a
No, I'm wrong.
b is ln a plus ln b.
No, log.
What's another log rule?
The ln a over b is ln
Or
of h.
ln, yes, because.
Yeah, that's true. Ln of a over b is ln a minus ln b. That's kind of like almost the same rule, pretty much. And then there's like one more important one.
The ln a
Exponent.
b, or b ln a is ln of a to the b.
Yeah, if you take the ln of a to the b, then you can just like pop that guy down, right? So that's b times ln a. For proofs of these facts, consult any Algebra 2 textbook, or it has a poster over there underneath the flag called Fancy Proofs of Log Property. It's just strain functions. All right, so anyone got a Teo? You didn't do anything yet. Just thinking.
Figure out what the first step is.
Okay, Calvin's like done already. I mean, hopefully you all did that first, right? Because like, duh.
Yeah.
Right.
Nothing's even multiplied.
Yeah, well,
Hmm?
Those rules have multiplication.
in that.
No, but they can combine log.
Can you like combine more?
That's definitely, that's pretty much the only thing to do right now, and it's also semi-obvious that that's what we should do, right? I mean, just put it whoosh, together. So we can write this as the limit as h goes to 0 of ln x plus h over x over h. Okay.
Oh, so that's just a ln.
Wait, did I lose anyone yet?
One.
Hopefully not.
0 over h, so 0.
Yeah, zero.
0. 0.
Oh, yeah.
What if I write this slightly differently in like a tiny minor way that sort of provides a hint? Does that have any new impact on your fragile brains?
Not.
Wait, am I missing?
Exponent rule.
It's like
reversed.
the other rule.
What other rule?
Over there.
Okay.
The one we haven't
Oh,
used yet.
but yeah.
Yeah, the one where it says you can
Yeah.
pop up the coefficient, right? The ln of x to the n is n ln x. So someone say it. What should we do?
Back up.
Pop up the 1 over h, right? Is that what you're talking about? Yeah, exactly. Oh yeah,
It's just like
things are happening now. So yeah, we could pop up the 1 over h, so this becomes the ln of
Wait.
x. What's up? No, I won't. I got that.
It's awesome. Now just now put that as 1 plus h over it.
Yeah, so that's what you were saying, right?
Yeah.
Yeah, this can be also just mildly rewritten as the limit as h goes to 0 of the ln of 1 plus h over x to the 1 over h,
Which is a familiar method.
which is starting to look kind of familiar now, right? Talk to me, class. What? Yes, me says it's like E. There's some like E going on around here, but not quite.
Can we pop the ln out?
Pop the ln out. You actually, yeah, you kind of could. But wait, before we do, yeah, not yet. But not yet. So, wait, thoughts? Some advanced moves required now. Not really advanced, just like kind of tricky and annoying. Like, what's going on? Talk, like, what is this? So Samin, you said this looks like E. Like, what is E? Maybe you should just, maybe you should just.
Define H as 1 over H.
H is like, H goes to 1.
So, sorry, tell me again. Limit as,
That's like H goes to 1.
can I choose a different letter? Like,
Like
you know,
X goes to 1. C.
C goes to 0 of,
1 plus.
yeah. That's something that we reviewed last week. Yeah, true. True story. So, how is that relevant to this? What's the problem?
Can you like set C for the H over X or something?
Yeah, basically, yeah, that's right. Yeah, we have this kind of X is like annoying, right? The X needs to not be here. I think I refer to this as the
Oh wait.
sand in the sunscreen.
Wait, didn't
This is annoying. It's not. It needs to go away, but it's not away. So we just have to do that thing. I already forgot who just said it. Was it you? Yeah. No.
I said like.
You said it.
Said like.
Yeah.
Put
You're right.
H over-
He says, let's define C to be, or whatever, pick any letter you want, as H over X. This will cause excellent things to happen. And then, if we're going to, so basically we're going to change the variable. We're going to change the variable from H to C. And what happens as H goes to 0, what happens to C? Wait. It also goes to 0, yeah, it also goes to 0. Okay, so whenever you're doing a limit switchy, when you change the variable, you have to figure out what it's doing as the old variable went to whatever it was going to. All right, so now, continuing this, we can rewrite this as a limit involving C's. You following this? Alright, so this H over X is just C, and then what's 1 over H?
X over C.
No, X, yeah, it's over C.
X over C.
No, I think you're all messing up.
1 over
Like
CX.
1 over CX.
Yeah, it's like H is like CX. So 1 over H is 1 over CX. Let's just ask 1. Are we cool?
Oh.
Okay, so what?
Pop out the X. Are we allowed to do it?
How about the 1 over X?
How about the 1 over X?
Yeah.
Yeah, it's like, just like.
Oh, yeah, and then we
Yeah.
can pop it out. Yeah.
Yeah, there's a bunch. Yeah, there's a bunch of things we can do kind of now. I mean, it depends on how many steps you want to skip and stuff. But one thing we can do is we can use an exponent rule that says that 1 over CX is really like the same thing as 1 over C times 1 over X. That's not an exponent rule. That's just like a rule. It's like a duh. But then the exponent rule says that if you have, something to the, like a to the mn, a to the mn is just like a to the m to the n. Yeah? So actually this is like a this.
Cool. Like bring down the 1
Yeah,
over
bring
X.
it down.
Now we can use a log rule, bring down the 1 over x. So we have the limit as c goes to 0 of 1 over x times the ln of 1 plus c to the 1 over c.
And then, like, 1 over X is a constant.
Yes, now Emma says we're taking the limit as c goes to 0, so x is a constant as far as we're concerned for the moment, right? So I can just take the 1 over x straight out of the limit. Is that okay with you?
Yeah.
Should be. So this is now 1 over x times the limit as c goes to 0 of the ln of 1 plus c to the 1 over c. Okay, now we're really, really close to being done.
That's easy.
Yeah, that's basically just lne. And if you want to get a little bit more particular about it, then there's a limit rule which says that if the limit of the log of something is the log of the limit of the thing. So actually we can write this as the ln of the limit as c goes to 0 of 1 plus c to the 1 over c.
Wait, what did that?
Yeah, how'd that like?
Oh wait, because that's just ln e then.
Because it's like one of those composition of two functions things, right? Like the limit of f of g of x is the same as is f of the limit of g of x. Because like, think about it, it's true. We definitely didn't do that epsilon delta proof. It was one of those ones where we just said, yeah, look in the appendix. All right, so, and this is just e. Are you impressed? This is kind of an awesome proof. So this is 1 over x times ln of e. In other words, whoa, holy crap. Not expected. The derivative of ln x is 1 over x. Pretty awesome. Was anyone predicting this?
No.
Really? Because it was a problem straight off your sketching derivatives worksheet, or just about. Top left-hand corner, kind of.
That's
Front or back?
positive and.
Yeah, that's like a double ln. But at least if you graph ln looks like this, right? ln x. So let's sketch what we think the derivative should be. Well, the derivative starts out as a huge positive number. Agree? So it's like way up here. What's the derivative at the so-called magic point? 1-ish or 1 for sure? Really 1. Why?
Because e to the x, like when it crosses 0, 1, its slope is 1.
Yeah. Why are you not using the phrase magic point? Yes. Eob says, let me translate. Eob says that since ln x is just the inverse of e to the x, then you're just taking the e to the x function, which we already showed has a slope 1 at its magic point. So the tangent line is being like reflected over the line y equals x. That was like a semi-crappy explanation, but this is definitely, the slope of the tangent line here is definitely 1 because that slope is 1, and it's like just gets reflected. So I know that the thing is 1, and then what happens is it stays positive but gets to be a smaller and smaller number. So, yeah. Pretty cool. Pretty cool. Okay, good, we learned something. Thing 3, triple product rule. Do it. This is a handy thing to know. Sometimes you have 3 functions all being multiplied together. What? Right. We discussed this?
No, I think it said it in the book.
Oh, really?
The book said it was like.
Oh, really?
It didn't say how, it just said it also works like this.
Oh, okay. Well, prove it.
Are we allowed to use like that? Are we allowed to use
Hint, multiplication is a binary operation, so there's really no such thing as multiplying 3 things together.
But
You can only multiply 2 things together and then more later. So that's pretty much the hint. So what do you
that's
do?
the entire
That's
thing.
like the
That's
entire
like-
That's the entire thing.
Yeah, it is. Kind of, but you still have to do it. So Alice, you were doing something with your fingers, say words.
You take the product of f of x times g of x and then each.
Yeah, so if we just think of that as like a function and then just apply the power rule to that, right?
Yes.
Or a product rule, product. So, they both start with P. I kind of just like use the wrong word a lot.
Yeah, you do a lot.
I like kind of like half the time. Yeah, I know. I keep doing it. Sorry.
Every single time.
He says, "Are you mean to your other teachers?" Really?
It's true. It's like who poured a little bit of Sydney in his cereal today?
Yeah, pretty cool. So then you get this beautiful formula. It's the derivative of the first times the other 2 plus the first times the derivative of the middle times the end plus the thingy. Alright, good. All done. All I have to do is make a song about it. Alright. Ready for thing 4. Have you noticed we're kind of just killing time today a little bit, doing weird little things? Good. We're going to have some homework due next class, and then next class we're going to do something that's like so awesome. It requires just like a fresh slate. So,
What is this?
and period 3 is behind us. So we're gonna now do some totally optional thing for 10 minutes. Are you ready?
We do
Sandeep.
times
Optional in the sense of I chose to do it, but you don't choose. Okay, we are going to prove a fact which was mentioned in the waning days of pre-calc C. But actually it occurs to me that if you were in 9th period, I think we never talked about this. Because I think we ran out of time one day and I just never got around to it. Did we talk about the reflection property of the parabola? I think I did in all the classes, but except for not the 9th period. Uh-oh. So here it is. The parabola has a property. And the property is, so here's like the directrix, and here's like the focus.
Oh my god.
Bet you thought you'd never hear these words.
Really?
The reflection property of the parabola says that if you have, so here's the focus, here's the directrix, if you have a ray of light which
Oh yeah, I
comes-
remember this. This was cool.
Yeah, I didn't do it, I did it in 2 of the 3 classes, but not the other class. If you shine a ray of light parallel to the axis of the parabola, then it will bounce off the parabola and go through the focus. And you draw a couple of these, you can see. And let's see, what other ones did I draw? Up here or something. Are you convinced? Ish?
Yeah.
Yeah. Okay, cool. So, and as we talked about last semester, if you were in one of those classes where we talked about this, this is kind of the entire science behind like satellite dishes. If you see them, they're like a giant dish and then there's like that little like dot thing in the middle that seems to be doing nothing. That is the focus of the paraboloid. And what it's doing is it's just taking all of the electromagnetic waves of information, I don't know what I'm talking about, and they all bounce off the parabolic dish and get, sent back towards the focus. And so what you're getting is a signal which is way, way stronger than if you just had like an antenna just sitting there out in the middle of nowhere. Alright, so notice that this requires some calculus is hiding behind this, of course, right? Because when I say bounce off, we know that when you bounce off a straight line, you do a thing that makes equal angles, right? So what does it mean to bounce off a curve? Well, you guessed it. You bounce off a curve is the same thing as like bouncing off a tangent line. I'm not really explaining this very well, but that's kind of what's going on, right? So, I just ruined it? No, we're going to prove this. And so what I have to do is I have to prove, I can do this in one, so there are 2 different ways to think about this. You can think about it as a light source located at the focus will send rays off, bouncing off tangent lines, and going parallel to the axis. Or you can think of it as the rays going towards the parabola, bouncing off the focus. But either way, what we must show is that these 2 angles are equal. That for any ray of light, the angle of incidence equals the angle of, what's that called, refraction?
Reflection.
Refraction?
We actually proved this in optics.
You proved this in the first day of optics, right?
No, the first